Hey guys, hope everybody's doing okay. What we're going to do today is look at intermolecular forces in covalent compounds. This is mostly a review from Chem 1. We'll go into it a little bit more in depth, and we'll introduce some new vocabulary as well, so we can make sure we write good answers to a lot of the FRQs that involve intermolecular forces. Okay, so let's get started. We already looked at ionic forces of attraction. That was an earlier lesson. We looked at metallic bonding as well. Those two are part of the same video or the same lecture. We talked about alloys a little bit with the metallic bonding. Now we're going to look at molecular substances or covalent substances. In a later lesson, we'll look at macromolecular substances or covalent network. And that'll kind of take care of all the substances we need to look at. So we're going to look at molecular. So we're going to focus on number 3 here on our list. And the properties vary greatly depending on the type of intermolecular force. So you could have molecular substances that are solids, liquids, or gases. Typically they're liquids or gases though, because we typically have weaker intermolecular forces holding together these types of substances. So the melting point varies from low to moderately high. Boiling point and evaporation rate varies. They don't conduct electricity, and they're fairly soft to brittle. So good examples of molecular substances: carbon dioxide, water, a lot of obviously non-metals being involved in molecular substances, a lot of carbon chains, alkanes, things like that. So we'll take a look at these as we go throughout the lesson today. So something we need to make sure we understand before we get going too much is our two categories of forces. We have intramolecular forces. These are forces within the molecule. Okay, they're the actual covalent bonds themselves. We'll talk about this when we look at covalent network in a couple lessons. But intra is within, okay? Intramolecular forces within the molecule. So I have the intramolecular forces labeled here, so you guys can see those. Let's change the color here. So we're talking about the actual chemical bonds, right? This is water, obviously. So the chemical bond between hydrogen and oxygen. That's a very, very, very strong attraction, okay? So those are very strong, but we're not going to be talking about those for the majority of this lesson. The majority of this lesson is going to focus on the intermolecular force, these dashed components. How is one water molecule as a whole attracted to another water molecule as a whole? Okay, but for right now, just take a look at what I mean by intramolecular forces here. It's the actual covalent bond. They're very strong, and they only break during a chemical reaction. So we actually looked at this. This was one of our lessons right after the halfway point of last unit, actually, where we looked at bond enthalpy, right? And we looked at how we break and form bonds, the energy required or given off when that happens. So that's when we're focusing on the covalent bonds themselves. For the rest of today and this lesson, let's focus on intermolecular forces. Another name for intermolecular forces, another name that you'll see is a van der Waals force. You don't see that very often anymore, but if you see it on an old worksheet here or there, it just means intermolecular force. So you can see the arrow pointing to those. We're talking about that dashed component here. What's the attractive force between two molecules? These are much weaker than the intramolecular because it's not an actual chemical bond. It's a force of attraction, okay? You're not actually sharing electrons here like you are in that covalent bond. And these are the forces that have to be overcome when a substance melts, going from a solid to a liquid, or boils, going from a liquid to a gas. So we have to overcome these forces of attraction. So our particles could be a little bit further apart in terms of a liquid, free flowing, or for a gas, very far apart, with basically no attractive forces between the particles. So let's predict which substance would have the stronger attractive force between molecules. So we have these two that are here. We have CCl4, so C and then 4 Cls. And then you have CHCl3. So a similar structure. Let's put the hydrogen up here. All right, and 3 chlorines. Okay? So predict which would have the stronger attractive forces between molecules. We have carbon with the same 4 components bonded to it. We also have carbon with 3 chlorines. And we're just swapping out 1 chlorine for hydrogen. How does that change these? Well, it changes this one over here. Well, this one is nonpolar because it's tetrahedral. All the bonds are to the same element. Okay, so all the poles are in equal and opposite directions. So nonpolar. Here, though, we're going to have dipole arrows going down, down, and down. There's really no dipole arrow pushing back up, right? So we're going to have a polar substance here. Okay, so how does the difference between a nonpolar substance and a polar substance determine attractive forces? How does that difference there determine which one is a stronger attraction? We're going to look at that as we go through the next couple slides. Okay, so you may recognize these from Chem 1. We have 3 main types of intermolecular forces. We have dispersion or London dispersion, dipole-dipole, and hydrogen bonding. We're going to take a look at London dispersion forces first. That takes up the majority of this discussion here, and then we'll look at the other 2. So a quick video clip on London dispersion, get a good visual, and then we'll go on from there.
Think about a can of seltzer, an aluminum can filled with water and carbon dioxide. All the particles of matter in this can of seltzer are at the same temperature. They have the same average kinetic energy. Why then is the aluminum can a solid, the water a liquid, and the carbon dioxide a gas? Why isn't aluminum a liquid or CO2 a solid at room temperature? Well, let's look inside the can. According to kinetic molecular theory, the answer lies in the strength of attraction between particles of a substance. Let's take a closer look. A carbon dioxide molecule contains 1 carbon atom sharing electrons with 2 oxygen atoms. CO2 can exist as a nicely symmetrical molecule. However, its atoms are constantly moving. As the shape of CO2 changes, electrons are attracted towards whichever end has a greater positive charge. A dipole is created. As the shape of CO2 continues to change, the location of the dipole also changes. This molecule is said to have a temporary dipole. A dipole on one molecule can induce a dipole on a neighboring molecule. This happens because the negative end of the dipole repels electrons in the adjacent molecule, causing them to shift position. The resulting force of attraction between 2 temporary dipoles is called, ironically, a dispersion force. This force is relatively small. Here's a model of condensed CO2. Some molecules have dipoles, others don't. Dispersion forces are present between some molecules. As energy is added to CO2, increased kinetic energy easily overcomes dispersion forces. Molecules move apart until, at room temperature, they exhibit the behavior of a gas.
Okay, let's take a look at helium, 2 helium atoms. Now, helium atoms aren't going to have much attraction for each other at all, but let's just say you have 2 helium atoms next to each other. Each helium atom has 2 electrons. And what you want to do is look at where those electrons are located. They're always moving, right? So you have these electrons bopping around the helium atom in their electron cloud, and then every so often you'll have these electrons, and normally want to stay away from each other, but they're always moving. You might have them next to each other for a split moment in time, okay? So look at the 2 electrons here on this helium. Okay, they just happen to be next to each other for a brief moment in time. For that brief moment in time, since they're next to each other, this part of the helium atom is partially negative, okay? Electrons are negative, they're over here together, negative. It means the other side here is a partial positive. What's that mean? It means if it comes near another helium atom, the partial negative charge on this one is going to create a partial positive right here, okay? And it's going to create a partial negative over there, okay? Opposites attract. So if you have a partial negative, it's going to be attracted to a partial positive. So it's going to kind of repel the electrons in this helium to the other end, okay, which would make this end right here partially positive. So and that only lasts for, what, a millisecond, nanosecond, whatever, a small snippet in time, and then it goes away because these electrons are always moving. So a London dispersion force is when you create a temporary or instantaneous dipole. So the electrons are close together for a brief moment in time, creates a temporary dipole, okay? And that will create a temporary dipole on the other helium atom, and for a split moment in time, they're attracted to each other. So London dispersion is attraction of momentary dipoles. Oops. Okay, momentary dipoles are temporary. Get that through the name, momentary, a brief moment in time, and they're constantly changing. So it's here, it's here, it's here, it's here, it's all over, okay? It happens very quickly. What we say here is that temporary dipole in helium atom number 2, for example, will induce or create a dipole in the other helium atom. Okay, so we're going to have a temporary or momentary dipole. It will induce a dipole in the other molecule. That's an important term I want to make sure we have. Okay, so dispersion forces are very weak, low melting points. So a lot of these, like carbon dioxide in that video, is held together with, well, it's really not held together, it's a gas. It has London dispersion forces as the main force of attraction. They're very weak, so it's going to be a gas already. Nonpolar molecules, that's key. Okay, nonpolar molecules and non-metallic elements are only held together by dispersion forces, like the helium atom on the previous slide. Okay, out of our 3 main types of intermolecular forces, London dispersion is generally, and I say the word generally because there's exceptions all over the place, so generally the weakest. Okay, so let's look at London dispersion forces and how the effective size, what that effective size is going to have on these. So the more electrons in the molecule, the more flexible the electron cloud is, higher polarizability. That is our new vocab term. Okay, we want to make sure we know what that is. Polarizability, if you want to write that in, look at the word. Part of it is polar, right? Polarizability is the ability of that substance to be polar, okay? If you go back here, helium's polarizability is not very big, okay, because it only has 2 electrons. So you need those 2 electrons to be relatively close to create your momentary dipole and to induce a dipole on the other atom. The more electrons you have, the better chance of creating that momentary or temporary dipole, right? It just makes sense. If you have more electrons, there's more of a chance that they'll be on one side of the molecule over the other side to create that temporary partial negative and then partial positive dipole, right? That's what polarizability is. Larger molecules have stronger dispersion forces because they're more polarizable. So we have to use this term when explaining London dispersion. I'll talk more about that in class when we practice. Additionally, molecules with pi bonds have higher polarizability because if you have a pi bond, that usually means you have a double bond, right? When you have a double bond, what do you have? You have delocalized electrons. What do those delocalized electrons do? They move around a little bit more. Since those delocalized electrons move, that electron movement may create a temporary dipole, which will create a stronger London dispersion force. Okay, so knowing just simply what a pi bond is, that's when you have a double or a triple bond. Knowing those electrons are delocalized and can move between the lobes of the pi bond, or even if you have a resonance structure, even that's going to create more of a temporary dipole for you. Okay. So let's take a second here and try one. Put the following in order of increasing boiling point. So, okay, let's think about this. I have bromine, fluorine, krypton, and helium. Increasing boiling point. Boiling point is going to increase when you have a stronger intermolecular force. So if the force of attraction holding the molecules together or atoms together is strong, it takes more energy to break that attraction. So weak intermolecular forces, low boiling point. Strong intermolecular forces, high boiling point. I don't memorize any of this. I know I think, okay? So if I have a very strong intermolecular force, I'm like, okay, what do I need to break that? Well, I need energy to break that. If I want to boil a liquid, I need to take the liquid and turn it into a gas. What happens then? Well, the forces of attraction are broken because liquids have some attraction, gases have basically none. So the stronger the attraction, the more work to break it and to boil the substance. So just think a little bit and don't really memorize. So take a second, try to figure this out. You can pause the video and see if you could do it. Look at the periodic table and look at the size, right? We're looking at that right now, of bromine, fluorine, krypton, helium, and see what you get. Okay, you can take a look at these. Boiling points are all here, okay? So if we're looking at the ones that we were focusing on, where are they? Bromine is here, fluorine, krypton, and helium. Okay? Krypton is, let's see, noble gas. It is level 4. Okay? Helium's in level 1. Okay? So definitely the lowest boiling point there. Okay? Helium is really, 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 really small. Look, it only has electrons in level 1. Okay? It's only 2 electrons. So I already mentioned this. The polarizability of helium is super low. So really low boiling point, like 4.6 Kelvin, super low. What's next? The next one is actually fluorine, which is in level 2. Okay, and where's bromine? Bromine is level 4 as well. Okay, so next highest is fluorine. That makes sense. It's a little bit bigger. It has 9 electrons, but it's F2, so it's 18 electrons. So it definitely can be more polarizable than helium, which is why the boiling point's higher. Now we have bromine or krypton. And you're going to say, well, they're both level 4. Okay, fine. Krypton has 36 electrons. Okay? Bromine has 35, but it's Br2, so it's double that. So it's 70 electrons. Look at that. Huge boiling point compared to krypton. Okay, so krypton is smaller because it's not diatomic, it's monatomic, so there's only one of them. So it's 36 electrons, 120.9. And bromine is, it's Br2, so it's definitely bigger. There's 2 of them, right? 2 bromines bonded together. Double your electrons, you have 70. Way more chance of partial dipoles being created, more polarizability right there. Okay, so that's what you want to look at. If you look at your halogens, F, Cl, Br, and I, you can see that iodine has, if we're just looking at the halogens, the highest boiling point. You're like, well, this, like, why is that happening? Students get confused by this because you tend to think iodine is so big that the force of attraction is pretty small. But what you have to think what you're comparing here. You have, if I said what bond is stronger, the iodine-iodine bond or the fluorine-fluorine bond, well, definitely the bond between fluorine is stronger, that covalent bond. We're not talking about that here. We're talking about London dispersion forces. So I have an iodine molecule right here, okay? That's going to be attracted to another iodine molecule, okay, over here, okay? This force of attraction right there is really strong because you have an iodine molecule here with 53 electrons in each iodine. So it's 106 electrons here, 106 electrons here. Big time temporary dipole that could be created, right? Whereas if I had a fluorine molecule, okay, attracted to another fluorine molecule right here, okay, the force of attraction between them, okay, again, that force of attraction we're looking at is going to be relatively low because each fluorine molecule only has 9 times 2, so 18 electrons here, 18 electrons here, compared to 106 and 106. So if you look at the halogens as well, fluorine, chlorine are both gases, okay, because the boiling point is so low. Bromine is a liquid at room temperature. because of the greater size and the greater London dispersion force, greater sense of force of attraction, iodine is actually a solid at room temperature, okay? Because those intermolecular forces between iodine molecules, that's important, between iodine molecules is really strong, okay? So it's really kind of neat how that all kind of makes sense. And you can see that gases, solid, and liquid, as your intermolecular forces increase because of our increasing size and polarizability, better chance you have at being a solid. The effect of shape is pretty easy to understand. I have a picture here of this two interlocking phone books. If you ever did that, you're going to waste a lot of your life doing that and try to pull them apart. It's really, really hard to do. You can find a bunch of clips on YouTube of people trying to do that. One's a Mythbusters clip I show in class sometimes. But anyway, that is why I have this here, because that ties into the effect of shape with London dispersion forces. So what we need to focus on for London dispersion forces, if we have a difference in shape, you want to focus on surface area. Okay? So more surface area means more possible places for dipoles to attract to one another. So I have 1, 2, 3, 4, 5, 6. So I have a 6-carbon chain here. This is be hexane, I guess. So I have hexane here. If it's attracted to another hexane molecule, look, there's 1, 2, 3, 4, 5, 6 locations for that to occur. So very flat, a lot of surface area for one molecule to be attracted to another one. Oh, sorry. So if two molecules have the same type of forces and a similar mass, okay, the one with more surface area will have a stronger attractive force. Usually this outweighs the surface area trend, okay? So go by mass first. That's why it has similar mass here. The one with more surface area will be stronger. So both of these are versions of pentane. They're just different structures, okay? So here's my pentane straight chain right here. 1, 2, 3, 4, 5 carbons. And here's neopentane, just a branched version of it. You can see, okay, they're both going to have the same formula, so they both have the same mass. So what's our tiebreaker if mass is the same or similar? It's surface area. So if you look at pentane, straight chain, 1, 2, 3, 4, 5 locations for dipoles to interact. Neopentane, you only have 1. Okay, so this has a stronger intermolecular force. This is a weaker intermolecular force. This would have a higher boiling point, melting point. This would have a lower boiling point or melting point because of the weaker London dispersion forces. Okay, so a straight molecule will have more surface area than a smaller size molecule that is curved or branched. So again, here are versions of pentane, so strongest intermolecular force to the left, weakest intermolecular forces to the right, based on surface area and places dipoles can't attract. So you can take a look at these. I have 3 versions of octane, it looks like. So match up the melting point to each one of these and go from there. Okay, so we have octane, straight chain, highest surface area. That will be 126, so that's going to be letter C right here. We have a branched octane, so it's still relatively flat, lots of surface area, so we're going to look at letter B for this one. And letter A will be this version of octane, because it is much less surface area, much less of a chance of the dipoles interacting. Okay, next one is dipole-dipole. Let's take a look at a video clip here that introduces that. And this ties in with hydrogen bonding. They're kind of one and the same.
Water is also a molecular substance. One oxygen atom shares an electron with each of 2 hydrogens. Its shape, however, is not linear, but angular. This angular shape creates a dipole in the water molecules as electrons are strongly attracted to the highly electronegative oxygen nucleus. Water molecules have a permanent dipole. This model of an ice crystal shows how the polar molecules respond to a large number of attraction forces. These forces don't come and go as they do with temporary dipoles. Intermolecular forces in water are much stronger than those in carbon dioxide. Even when heated to room temperature, water molecules cannot completely overcome the attractive forces. They are held together sufficiently to exhibit the behavior of a liquid.
Okay. So, dipole-dipole, what's that mean? It means you have to have something with dipoles. Okay, what's dipole mean? Dipole means polar. So, key point here. In polar molecules, which have a permanent dipole, the partial charge of one molecule is attracted to the opposite partial charge on another. So I have chlorine attached to hydrogen, so I have HCl. It's definitely polar. Chlorine is your partial negative. Hydrogen, partial positive. If another one of these happens to be in the area, the partial positive on hydrogen will be connected to, not connected, will be attracted to the partial negative on chlorine. So opposites attract, okay? The bigger your dipoles are, the larger they are in terms of like magnitude, like polarity, the stronger this is going to be, okay? So HCl is relatively polar, but if there was another atom here, like HF, which we're going to look at next, that would have a stronger attraction because fluorine is a greater electronegativity. The difference will be bigger. So this is much stronger than dispersion for similarly sized structures. Okay, that's important because you're going to see a lot of examples where you have a really big structure, like octane on the previous slide or 2 slides ago. And even though octane is London dispersion only, it will actually be an overall stronger intermolecular force than maybe some smaller molecule that only has dipole-dipole as its main attractive force. Okay, so this is much stronger in general than dispersion because the permanent dipole is more intense. All right. So moving on to hydrogen bonding then, the last of our 3. Here's HBr. Electronegativity values from your table, 2.1, 2.8. Difference is 0.7, so it's polar. So partial negative on the bromine, partial positive on the hydrogen. You find another one, okay, another one comes nearby, and look what happens. They're attracted to each other. This is the dipole-dipole attraction, okay? It holds them closer together. The stronger that is, the better these can stay together and potentially be a liquid or a solid. Okay? HF though, H is a 2.1, fluorine is a 4.0. Look, difference is 1.9. This is a humongous difference. So I tried to highlight that here. And look, I gave you the partial negative dipole here, and then the partial negative dipole here is much bigger. So the stronger dipole is on HF, okay? What does that mean? Another HF comes along and it's attracted to it, right? And look, I tried to again highlight the difference here. So you have your dipole-dipole attraction here, much weaker than the dipole-dipole attraction here, okay? So the HF has a much stronger dipole-dipole attraction, and because hydrogen's involved, this is actually a hydrogen bond, okay? Don't get me started about how a hydrogen bond isn't really a bond, okay? Let's just add another layer of confusion to everything. So a hydrogen bond is not a bond. I'll say it in class a million times, it'll be really annoying about it. A hydrogen bond is a force of attraction, okay? You need to know that. So a hydrogen bond is a force of attraction. They call it hydrogen bond because, okay? They're trying to throw you off, I guess. I don't know. But that's what it is. Okay, so it's just a force of attraction, an intermolecular force, not intramolecular anything. Okay? So here's the rules, though, for hydrogen bonding as we get near the end of this. A couple rules for hydrogen bonding. We went over these in Chem 1, so just a reiteration of all that. A hydrogen bond is simply a strong dipole-dipole. When hydrogen is directly bonded to F, O, or N, remember those are our top 3 electronegative elements, NO and F, NOF or FON, however you want to remember it. There's a large electronegativity difference. You saw it over here. Electronegativity difference, 1.9. Over here, 0.7. Okay? So you get that big electronegativity difference. This causes a very strong partial charge. the large dipoles between molecules are strongly attracted to form the hydrogen bond, which is again that. Okay? Strongest of all intermolecular forces. That's key to remember as well. Again, if your molecules are a similar size, hydrogen bonding is strongest, dipole-dipole is next, London dispersion is the weakest. If you have really big differences in size, a lot of exceptions to those rules come into play. So don't be a robot and think hydrogen bonding, dipole-dipole, London dispersion, and that's how you live the rest of your life. You have to be aware that there are exceptions to these. Okay, so circle the hydrogen bonds in this picture. There are quite a few. So you take a second and do that. Okay, so if I change the color so you can see it, there's one right here, 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 here. Okay, 4 hydrogen bonds in this picture. And those are just a couple that it shows. Okay, that takes care of this main lesson here on the 3 types of intermolecular forces. So what do I want to make sure you know from this? A lot of it's a review from Chem 1. Okay, you saw some of this and I get that. But I want you to be aware of the term polarizable or polarizability from London dispersion. Okay, so when you're explaining something in terms of strength, if you're explaining the strength of London dispersion forces, you need to mention polarizability in that explanation. If you just mention that an atom is bigger, so therefore the intermolecular force is stronger, it's not good enough. An atom is bigger, therefore it is more polarizable, therefore the intermolecular forces are stronger. So I'll have a little cheat sheet, like little guide on the board for you in school with things to focus on. That's going to be one of them. Something else I want you to make sure you get from London dispersion is the temporary dipole, and it induces a dipole on another molecule. So you have your temporary or momentary dipole and an induced dipole. So when one molecule is polar and another molecule is next to it, the polar or the partial positive, partial negative on the one atom or molecule will create a partial dipole, a partial positive, partial negative, temporary dipole on the other molecule or atom. Okay, so I want to make sure we understand that as well. So to wrap this up, you can arrange the following by increasing melting point. Okay, we actually did one similar to this, maybe the same one in Chem 1. So you have these 4 structures. What you want to do is, since you're basing on a melting point, you want to figure out which one has the strongest intermolecular force, which one has the weakest intermolecular force, and go from there. Okay, so the strongest intermolecular force, highest melting point, weakest intermolecular force is the lowest melting point. We could go over it a little bit later or in class, and we'll see how we do. Okay, give it a try, and we'll talk about it when I see you. All right, hope this made sense, guys. Thanks. I want to quickly review the practice problem from the end of the last presentation, though, just to recap this so you have an understanding of it for today. So you have a bunch of substances, right? It says arrange the following according to increasing melting point. All right. So when we talk about melting point, we're going from what to what? Well, we're going from a solid to a liquid, right? So in order to go from a solid to a liquid, we need to break some intermolecular forces. So, your solid has, all of its particles are very organized, right? Like this. They vibrate in place. There's not a ton of movement there. Okay, that's your solid. And then you're going to go to a liquid where these attractive forces between these particles, aren't as strong. So here's your liquid, they're more spread out. This is like, I don't know, the 5th day of school. We talked about some of this stuff. These are horrible particles, sorry. Okay, so we're going from solid to a liquid here. In order to go from solid to a liquid, we have to break those intermolecular forces. So the easier it is to break those intermolecular forces, then the easier it's going to be for something to melt, right? If it's really difficult to break these, then obviously it's going to be harder to melt that substance. And it's going to stay in the solid state for a longer amount of time. So a melting point, we're going to look at it again today. We'll tie it in with boiling point, same idea. We want to look at the strength of the intermolecular forces that these things have. So I look at these, and I look at that first one, that is magnesium oxide. And the first thing I notice is that it starts with a metal, and then it has a nonmetal. So as soon as you have a metal and a nonmetal, I'm done thinking, and I know that that's ionic. Okay, ionic compounds, like ionic bonds, really strong. Okay, stronger than any of the intermolecular forces that we talked about in the previous lesson. Intermolecular forces are really associated with covalent molecules, which is what the rest of these things are. So I look at the rest of them. I have CO2. Now I know from experience, I know that CO2 is C double bond O with some lone pairs, and then double bond O with some lone pairs. I know it's nonpolar. That was one of our examples in the polarity lesson. So I know it's nonpolar. There's no hydrogen bonding or dipole-dipole then. So this has to be London dispersion forces only. So London dispersion forces. Same thing with oxygen. I know oxygen is O double bonded to O with some lone pairs on each oxygen. Obviously it's nonpolar, so there's no hydrogen bonding or dipole-dipole moment. So again, London dispersion forces. And then water is our main example for hydrogen bonding. You probably knew that from bio. So we have hydrogen bonding here. These are all the primary intermolecular forces, right? So like water has hydrogen bonding, dipole-dipole, and London dispersion, but the main one's hydrogen bonding. So which one of these is the strongest intermolecular force or strongest force? Well, it's going to be magnesium oxide, right? So that's going to have the highest melting point. So that is going to be, out of the four of them, that is going to be the one that's the highest melting point. Which one will have the next highest melting point? So you're looking at which one is the next strongest intermolecular force. Well, it's going to be water, right? So water has hydrogen bonding. That is stronger than, in general, stronger than dipole-dipole and London dispersion. So that is next. And the last two are London dispersion. So which one of these is the stronger intermolecular force? You may remember from the previous lesson that a stronger intermolecular force with London dispersion has to do with the number of electrons, which is tied in with the molar mass. So obviously CO2 has an extra carbon, compared to O2. So CO2 is more massive, has carbon in it, so it has 6 extra electrons compared to the oxygen here. So this is going to be the next highest melting point, and then oxygen will be the lowest. All right, so that brings us to one of the choices over here. But I just want to recap that really quick. Ionic is the strongest. We go into a couple more attractive forces in AP Chem, but this is all we worry about for right now. Hydrogen bonding is next, and then London dispersion with CO2 and O2. Makes sense, right? Magnesium oxide is a solid, water is a liquid, CO2 and O2 are what? Well, they're gases, right? So of course it's going to be harder to melt MgO than it is to melt O2 or CO2 because they're already melted and boiled already, you know what I mean? So anyway, that takes care of that.